In this video, we'll discuss the chain rules derivation. I'm going to restate the chain rule a couple of different ways, and then we'll use one of the limit definitions of the derivative to compute or to show that the derivative of a composite function can be found using one of these formulas. So here's just a restatement of the chain rule, the one that we're interested in. So the chain rule says that if y is a function of u, and that function is differentiable at u equals g of c, and u is a function of x, and that function of x is differentiable at x equals c, then the derivative of y at x is just the derivative of the outside function evaluated at u times the derivative of the inside function with respect to x. It's almost as if these two reduce. They don't. This is a separate function from this, but we can almost think of them as canceling out and giving us this dy dx. Now, an alternate notation is this. This is the derivative with respect to x of the outside function, which is f, evaluated at the inside function, which is g. And this says take the derivative of the outside function and evaluate it at the inside function. We're using the notation u for that here. We're using the notation g of x for that here. So we just have f prime of g of x times the derivative of the inside. Du dx is the same as g prime of x. So we've got that. And this is the form I tend to use, but this is a very common form as well. And this is the limit definition of the derivative that we're going to use. I'm interested in the derivative at x equals c. So I said the derivative of f at c is the limit as x approaches c of the change in y over change in x. So f of x minus f of c divided by x minus c. And we could also use this derivative if we wanted to. But I feel like the derivation is a little bit simpler if you are letting x approach c. These are the two limit definitions of the derivative. And this time, this particular one is going to be most relevant to us. So we're interested in the derivative with respect to x of this f of g of x. While using this form of the derivative, let's say we're evaluating this at x equals c. This is the limit as x approaches c of f of g of x minus f of g of c divided by x minus c. If we take this expression and we multiply by g of x minus c, or g of x minus g of c, divided by g of x minus g of c, then we get this expression. If I regroup this, I've got f of g of x minus g of c. I can put this as my denominator here. And then I can put this as my denominator over here. We know that the limit of the product is the product of the limits, that the limit of this function times the limit of this function is equal to the limit of the original function. And remember, we can do this. What I just did was legal because I just said this times this is that numerator, and then this times this is that denominator. We just switched the order of these two factors in the denominator. Now, if I take the limit as x approaches c of each of these, we're almost there. This factor is g prime of c. Now this factor, I think, should be f prime of g of c, but I need to make sure that that's valid. So this expression looks almost exactly like that expression, except instead of an x, we've got a g of x, and instead of a c, we have a g of c. And now that's the same in the denominator. So that pattern matches as long as the limit as x approaches c of g of x is equal to g of c. So the claim I want to make is that this limit is equal to this limit. And I believe that that's acceptable. We can do that. And the reason that we can do that is that differentiability implies continuity. So if a function is differentiable, if this derivative g of g at c exists, then as x approaches c, g of x approaches g of c. So this limit is equal to this limit, and this is defined to be f prime evaluated at g of c. And this is f prime of c, or excuse me, g prime of c. And that's the derivative of f of g of x at x equals c. So in general, with all the c values for that, where all of these, the fine print hold for the inside function is differentiable at the limit point of the other one, then the derivative of f of g of x is equal to f prime evaluated at g of x times the derivative of the inside. And that's our chain rule.